All right, let's dive into a world that's, right at the very edge of what we can even see. A place where scientists have been chasing these mysterious shapes hidden deep inside tiny particles. It's a story about a nanoscale puzzle, really, and a brilliantly simple fix for a super complex problem. So, for years, right, you've got researchers peering through these incredibly powerful electron microscopes, and they keep seeing the same thing over and over again. These really strange, kind of beautiful patterns. Some look like bow ties, others more like butterflies. They knew these shapes had to mean something important, but the big question was, what exactly were they looking at? Well, it turns out the culprit is this absolutely fascinating structure called an icosahedral twin, or, icotwin for short. Now, icosahedral, that's a big word, but it just means it's related to a 20-sided shape, kind of like one of those dice you'd use for gaming. And this thing, it isn't just a simple crystal. Nope, it's got a secret identity. Okay, so think of it like this. You start with just a tiny little cluster of atoms, all arranged in one specific way. But as more and more atoms pile on, as this thing grows, that original shape gets, it gets strained. It becomes unstable. So to fix this problem, the atoms do something really clever. They completely rearrange themselves into a perfectly coordinated pair of crystals, a much more stable, much stronger twin structure. And this whole transformation, it happens in a few steps. First, you get that small atomic cluster. Simple enough. But as it gets bigger, the pressure inside starts to build and build until, bam, it hits a tipping point. Then everything realigns into that new, super stable twin shape. And that's the moment that creates those telltale bow tie and butterfly patterns that scientists were seeing all along. But wait a minute. This led to a bit of a puzzle. I mean, if this transformation is pretty common for a lot of metals at this tiny scale, why was it so incredibly hard to find these icotwins reliably? Why weren't researchers just seeing bow ties everywhere they looked? The problem, it turns out, is all about perspective. See, a single sample has millions of these little nanoparticles, all just tumbled together in a totally random jumble. So seeing that signature pattern, it was a complete game of chance. You had to have the microscope pointed at the exact perfect angle. We're talking a fraction of a degree off, and poof! The bow tie pattern just vanishes. And trying to actually calculate the odds of getting that perfect view? I mean, in the researchers' own words, it was incredibly complex. The geometry of the crystal, how it plays with the electron beam, it was just messy. This quote here really drives home just how ridiculously daunting the physics behind it all was. So here's the crucial point. Trying to tackle this with raw, brute force math, it was basically impossible. They needed a smarter way, a more efficient way to figure out the chances of actually spotting one of these things in a random sample. They needed a shortcut, and a really clever one at that. And their breakthrough, honestly, it's as elegant as it is effective. They call it the paint method. And instead of getting totally bogged down in complicated equations, they decided to just map the whole problem out visually. They created a complete map of every single possible viewing angle for one of these particles. The absolute beauty of this method is how simple it is. So they have this 2D map of all possible viewing angles, right? Then they basically paint in all the specific angles where you'd actually be able to see the bow tie pattern. The final step? You just measure the total painted area. That little fraction of painted to unpainted space, that gives you the exact probability of spotting an icotwin. Genius. So the big question, right? Did this clever paint method actually work in the real world? The team put their model to the test, and the answer was a huge, resounding yes. Their model predicted that even for pretty large nanoparticles, we're talking up to 50 nanometers wide, that signature icotwin pattern should be visible in over 2/3 of them, even when they're all randomly jumbled up. That messy, random problem of chance? All of a sudden, it was predictable. And if we break it down even more, you can really see how well this thing works. For the smaller particles, the ones under 20 nanometers, the chance of spotting one is a staggering 95%. 95! And even as they get bigger, up to around 50 nanometers, the probability is still incredibly high, over 66%. The paint method had absolutely cracked the code. Okay, so let's bring this all home. We started out with a mystery, right? These weird bow tie patterns showing up under a microscope. Now we know what they are. They're the signature of these amazing shape-shifting structures called icotwins. For years, finding them was a total game of chance, all because of their random orientation. But then, this brilliant paint method comes along, creates a predictive map, and solves the whole problem. This breakthrough means that finding these absolutely crucial nanostructures is finally reliable, and that opens the door to understanding materials on a completely new level. And that brings us to the most exciting question of all. Understanding a material's atomic structure, that's the key to unlocking what it can do. So now that scientists have a reliable way to find and study these fundamental ico-twin structures, what new secrets are they going to reveal? What new materials, what new technologies could this discovery lead to? The hunt, my friends, is really just beginning.